Well, hello class. This is your well-rounded math teacher, Mr. Bakar, and today we're going to be covering some exponential functions. Here's a word problem that deals with it a little bit. Sam is working in a biology class with a petri dish of bacteria. He estimates he has a colony of about 25 bacteria. Assuming the entire population of bacteria doubles every hour, find how much bacteria Sam will have after 5 hours. Okay, we can kind of set up a little table for this. First of all, the initial amount would be at 0 hours. Not an hour, but 0 hours. We're going to have 25 bacteria. After 1 hour, we're going to double that. We're going to have 50 bacteria. And then so on and so forth. 2 hours, you'll have 100. After 3 hours, you'll have 200. 4 hours, 400. And finally, after the 5th hour, you'll have 800 bacteria in the petri dish. Now, when it's just 5 hours, 10 hours even, you can set up little tables like this. But when you get to maybe 100 hours or 200 hours, you're not going to want to set up a table like this. You're going to work with the exponential growth here, the exponential function. One way you could look at the amount of bacteria in the dish is this. Y equals, you're starting out with your initial amount, 25, but you're doubling it, so times 2 every hour. And in this case, it'd be 2 to the 5th power because you're multiplying by 2 5 times. This is kind of set up in the form of the exponential functions we're going to work with, which is y equals a, which is your initial amount, times b, how much it's getting doubled by or increased by every time, to the x power, which leads us to this. If you have an x or a variable in the exponent, it's what we consider an exponential function. So this is what we're getting into today. We're going to graph these a little bit, maybe solve a few equations, but exponential functions. We've worked with some other functions just to kind of reiterate here a little bit. Linear functions, of course, it's going to be x to the 1st power. Quadratic functions, you're working with y equals something like x to the 2nd power. Here this would be an x cubed, x to the 4th, and x to the 5th. The variable is not the exponent. You can see our exponents are 1 here all the way up to 5 over here. We also worked with some square root functions and some rational functions. That's what chapter 8, this last chapter that we were in. Okay. And chapter 8, dealing with rational functions, working with your vertical asymptotes and any holes, and then square root function, using the domain and range to find that first initial value that you're going to graph in order to graph your square root function. So now we're getting into exponential functions. A and B right here are just numbers, they're constants, and your actual variable is your exponent, hence that's exponential functions. And I kind of showed you how we used that in the last problem. But anyway, some properties of exponential functions. Function is continuous and one-to-one. For every x, there is one y. Domain is a set of all real numbers. This is going to be true for all of them. The range, not so much, but the domain is always the set of all real numbers. The x-axis is the asymptote of the graph. If you look at these two graphs down here, these are two exponential functions. One's growth and one's decay, and we'll talk about that a little bit. As this graph comes down here, it will not cross the x-axis. And this one over here, it's kind of coming down as x increases. But once again, it doesn't cross the x-axis. That's always going to be an asymptote for your graph. The range is a set of all positive numbers. Is a is greater than 0 and all negative numbers a. So here it is. Your range is either y is greater than 0 or y is less than 0. It's one or the other. It's not the same. And it's never going to equal 0 because that would be your x-axis. So that's your range. the graph contains a point 0a. This is your y-intercept. Whenever you plug in 0 for x, anything to the 0 power is 1. So a, whatever a is here, is always going to be your y-intercept. The graph of y equals ab to the x and y equals a times 1 over b to the x power are reflections of each other over the y-axis. And if you look at this graph, this is 2 to the x power, and this is 1/2 to the x power, just the reciprocal of it. These two graphs are reciprocals, or reflections of each other around the x-axis. So we'll be getting to that also. So just graphing one. Sketch a graph of y equals 3 times 2 to the x power, then state the functions, domain, and range. Okay, so we got a little table here that we'll be filling in. One way you can do this, you can plug these into your graphing calculator and hit table and generate your values, but I'm going to show you kind of where these values come from. First of all, plugging in x equals a -3 for our function, y equals 3 times 2 to the x power, our exponential function. This would become y equals 3 times 2 to the -3 power. Well, you can't evaluate negative exponents. How do you make negative exponents positive? You flip them around the fraction bar. So really what this is 3 all over 2 to the 3rd power, or 3 all over 8. If you plug that in your calculator, that's about 0.375. Okay, -3, 1, 2, 3, 3.75, 0.375. We'll say it's right about there. Now, you can do this. Just plug this into your graphing calculator and it'll spit out your answer. You don't have to work with the negative exponents so much. So 3 times 2, then hit your little caret key and plug in -3. If you plug it in exactly like this, make sure the 2 is in parentheses. You should get 0.375 out on your calculator. Plugging in -2, I get 0.75. Plugging in -1, 1.5. Plugging in 0, let's try that. Y equals 3 times 2 to the 0 power. Now I said a, this 3 right here, is always going to be your y-intercept. Well, here's why. Anything to the 0 power is 1. So this actually becomes 3 times 1, or 3. So 0, 3, which is right here, is my y-intercept. So a is always going to reveal your y-intercept, that 3 right there. Plugging in the other points, 0.75, 1.5. You can see we're kind of going up here. Plug in 1. Y equals 3 times 2 to the 1st. That's going to give me 6. And y equals 3 times 2 to the 2nd. 2 squared is 4. 4 times 3 is 12. Graphing those also. 1, 6. Double it up right there. Double 6, you get 12. It's going to be up here somewhere. Kind of off the graph, so we don't really have to worry about it. And our graph is growing exponentially. There it is. And once again, this will never cross the x-axis. So there's our graph, exponential growth. It's a little bit different than most of our graphs. Domain. Well, it's never going to cross the x-axis. Well, actually, I don't have to worry about that. Domain is all reals. And range, your y values. Y has to be greater than, in this case, 0, because your x-axis here, where y is equal to 0, is kind of like a horizontal asymptote. It never crosses the x-axis, so y is greater than 0. Now, if this would have been -3 up here, that would have flipped our whole graph upside down, and it would be kind of opening up like this. Our domain would still be all reals, but our range would be y is less than 0. All your values of y would be less than 0. So that's the difference between having a positive a and a negative a. Okay. Sketch a graph of y equals 2 times 1/2 to the x power. Now, this is an example of decay because b in this case is a fraction. In other words, it's between 0 and 1. If it's between 0 and 1, it's going to be decay. Doesn't even matter what's in front here, too, except the b, or I'm sorry, the a, has to be positive or it's going to be opening down, and we want it to open up our graph. So plugging some numbers in here, I'm going to get y equals 2 times 1/2 to the -3 power. Best way to do this one is probably plug it into your calculator. It'll figure it out for you. In this case, we are going to get 16. Plug in -2, 8, 4, 2, 1, and 1/2 are all my numbers that we would get plugging these in for x over here. So -316, way off the chart up here somewhere. -2, 8, right about there. -1, 4, about there. 0, 2, there's our y-intercept. Once again, a is going to be your y-intercept. 1, 1, and then 2, 1/2. So instead of going up like our last graph did as x gets larger, now it's going down. This is an example of exponential decay instead of exponential growth. So that's what it is when your your b is between 0 and 1. It's a fraction. So exponential growth and exponential decay, I kind of talked about those a little bit now. It's the same formula for both of them. Y equals ab to the x power. The first thing here is this: a has to be positive. It has to be greater than 0. If it's a negative number, then your graph is going to be opening down. It's going to be below the x-axis, and we don't want that for growth or decay. But for growth, the main thing with growth is b. b has to be greater than 0. It has to, I'm sorry, not 0, 1. b has to be greater than 1. As long as it's greater than 1, not equal to 1, but greater than 1, it's going to be an example of exponential growth. Whereas with decay, first of all, a has to be positive again. That has to be greater than 0. b has to be less than 1. It's got to be a fraction. But it can't be negative, so it's got to be greater than 0. So if b is between 0 and 1, not equal to 1 or equal to 0, anything like that, but less than 1 and greater than 0, you're going to have an example of exponential decay. Something like that, a lot of times you'll see as, we'll say a is 5, whatever, as long as it's positive. 1/3 to the x power, example of exponential decay. Or y equals 7 times 0.8 to the x power. Once again, 0.8 is between 0 and 1. It's an example of exponential decay. Some examples of exponential growth and decay. Well, if you look at a car, when you buy it brand new, it's worth as much as it's ever going to be worth. And each year after that, the price of the car goes down. That would be an example of decay. Gold, usually the value of gold, no matter what, goes up. Every year it goes up a little bit more, so that would be an example of growth. For the most part, housing, when you buy a house, when you sell it in 30 years, the price has gone up quite a bit. Housing is usually an example of growth. And the value of your computer, well, you know this. It's not worth half as much the next year. So that also is an example of decay. So growth and decay. So determine whether each function represents growth or decay. So looking at this one, 1/5 is to the x power, so that's your b. My a in this case would be 1 here. If there's nothing there, it's 1. 1/5, your b now is less than 1 and greater than 0, between 0 and 1. So it's an example of decay. Here, a is positive, so that's good. Looking at the b, my b is equal to 1.2. In this case, b is greater than is 0. Oh, I said 0 again. It's supposed to be what? 1. If it's greater than 1, it's an example of growth. So this bad boy right here is growth. And that's about it. We'll be finishing the notes up tomorrow in class. I'll see you then.